Hello. So this video talks about the whole issue of averaging velocity vectors to get an average velocity and some of the misconceptions that can come out of that. And it also deals with calculating an average acceleration in a curved path situation. So once again, the stress is always on the definitions. In these examples, the fundamental constraint of all these problems is simply the definition. The challenge for many young people comes with the technical definition of that in any given question. What is the difference in velocity? What is the difference in time? And making sure that you calculate those things properly. So hopefully this is helpful to you in your studies of two-dimensional kinematics. So before we begin working with velocities in 2D, let's remind ourselves a little bit about 1D. The definition of the average speed is the total displacement divided by the total time. And we have to remember, this is absolutely critical in technical sciences, that we remember the definitions. Not what we think it is, not what maybe it kind of was in the past, but what this specific definition says. And you need to spend time and you need to memorize these things. These are deltas, they're not differentials. This is a finite difference when it comes to average. Now let's suppose we have an example here where we have a car that has these three different velocities: 20 meters per second for 10 minutes, 25 meters per second for 5 minutes, 10 meters per second for 15. A mistake comes when a youngster isn't adequately prepared, does not read the notes, and you fall back on your original knowledge by simply averaging the velocities and ignoring how long we spent at each of those velocities. Okay? And that is wrong, and it will never work out except if these times are all the same, which they usually aren't. We don't want to remember special cases. We want to remember the definition, the fundamental definition. So here we would have an example where a student would add up the three velocities, divide by 3, and get this answer. And to be completely clear, this is wrong. And we're not to do that. It completely contravenes this definition. What we do instead is we look at how far did the car travel in the first interval with displacement 1. Well, we know from our previous work that the speed times the time, or the velocity times the time, will give us the displacement. So we have v1 t1, and we add that to v2 t2 and v3 t3. So 20 times 600 seconds. Remembering we have to be in MKS units. We cannot leave it in minutes. Okay, we use standard units always. 25 times 300 and 10 times 900. So you'll see here where I wrote it out, I've got 12,000 meters, 7,500 meters, 9,000 meters. And I'm dividing by the total time, which is what the equation says to do. 600 plus 300 plus 900 is 1,800. When you do the arithmetic, you get 15.8 meters per second. Now this is less than this average because we spend half our time going this slow. And that's what this system fails to consider. No matter what I put for my times, you'd always get the same answer here. I could put 1 minute, or let's say 1780 seconds here, and 10 seconds and 10 seconds. I would get exactly the same answer as I do here, where this would change quite a bit. So again, not that difficult an idea, but it is absolutely critical that we remember the definitions. As we move into 2 dimensions and other things, we base our knowledge of those things on these fundamental ideas. So it is very important that the young student of the subject understands the definition and how to apply it. So let's consider a question now where we have 2 velocity vectors, one traveling in this direction, and then the thing turns and goes in a different direction. And after a prescribed period of time, we want to know what the average velocity would be. not only the number, in other words how many meters per second, but also the direction. Now remember, that's absolutely critical with vectors, that we consider direction as well as magnitude in every situation, unless explicitly told not to bother. Now this takes getting used to, and many young people starting off with these concepts will forget the direction because it's a new idea. And all I can say to you is you just got to do lots of practice till you get used to it. Let's have a look at this question here. The first velocity is 30 kilometers an hour at a compass bearing of 50 degrees. The second velocity is 15 meters per second, east 5 degrees south. The first velocity acts for 10 minutes, the second one acts for 5. And we're asked to compute the average velocity. Now, notice that this doesn't imply direction or magnitude. When you are given to compute an average velocity and you know it's a vector, it's incumbent upon you to know in advance that you must compute both magnitude and direction. And the direction that you're going to compute in this case ultimately has to be a navigation direction because this is a navigational type question. Our first step here will be to clean up the givens. We're going to convert everything to MKS units, meters, kilograms, and seconds. So our timing goes from minutes to seconds and minutes to seconds. Please make sure that you have your conversions correct. Don't make silly mistakes like saying there's 60 seconds in 10 minutes and things like that. The 30 kilometers an hour divided by 3.6 gives you 8.33 meters per second. This one is okay. And then we switch now to converting our angles to the XY or theta angles we need to do calculations. Theta 1, the angle here, is going to be 450 minus 50, which is 400, and then subtract 360 to bring it in a range, gives you 40 degrees. East 5 degrees south, we can reasonably figure this out. We know that east is the plus x direction, and we're 5 degrees south of that. That would be like -5, but we're not allowed to use that. So we have to go all the way around, and we end up with 355 degrees. The next step, after we have everything converted and we have our XY angles, is to calculate the components. And these are always going to be magnitude times cos of the angle for x and sine of the angle for y. So you can see here, in the case of V1, we converted the 30 kilometers an hour to 8.33 meters per second. That goes here, times the cos of 40, which is the angle for number 1, gives us plus 6.38. And for the sine angle for the y-axis, plus 5.35. Similarly, for the second one, we have 15 meters per second times cosine of the angle 355. Gives us, in this example, plus 14.94 for the x, which seems reasonable. It's going to be going in this direction. And then just a small amount of y motion, because it's almost traveling purely in the x. And we end up with negative 1.31. All of these, of course, in meters per second. Now the next slide will show how we go on to finish this calculation and to actually compute the average velocity in this case and convert it to navigational values. So these are the components that we computed on the previous slide. And now we're going to follow through with the definition. The only difference now is we have to calculate the displacement in the x and in the y separately. The displacement in the x then will simply be velocity 1, x component, times the time in the for the first velocity. Velocity 2, x component, times the time. And you can see that the 6.38 comes right across, coupled with the 600 seconds. 14.94 v2x here comes across, and the 300 seconds. We also had, and then that's just arithmetic, and we get 8,310 meters. It's positive because that's the direction. Exactly the same procedure with the y. v1y is 535. I'll go here, again the same time. v2y, and then the same time again, and we get in this case 2817. So this is the difference, the amount of change in displacement that has occurred over this interval, where these two velocities were acting over the times that were given. So now we calculate the average x and the average y separately. Once again, we keep them separate. So it's a straightforward extension of the definition we already have seen. So I take my 8300 and I divide it by the total time, and I get 9.23 meters per second. I take the total y displacement and divide it by the time, and I get plus 3.13 meters per second. If I was to state this velocity vector as an ordered pair, it would look like this. Hopefully it'll show up on the side here. But this is not sufficient because this is a navigation question. So while this is a correct answer from the standpoint of the velocity vector, given that this was a navigation question with navigation style angles to it, this is not in a form that is meaningful to the question asker, so to speak. So there's an obligation, perhaps not stated, for us to convert this vector into a form that is more readable. Now, if on the other hand you're given a question that hasn't got navigation connotations to it, you could leave it like this. It'd be perfectly fine. You do not have to convert these things to polar form unless specifically requested or implied by the question. So this is just a worked example of converting from rectangular coordinates to Cartesian, just to be explicit. This was the answer we got in the last example. So we're going to compute the 2 norm here to get the magnitude. Notice there's no plus sign here because magnitudes are always positive and there's no direction. This is a scalar. We take find the theta angle here. Both of these are in the first quadrant, so the conversion of the angle from the answer is 0. We don't have to change it. The calculator tells the truth. We get 18.7. We'll round that to 19 for simple math. And then converting to gamma 450 minus this and putting it into 360 range, you get 71 degrees. So our final answer is 9.75. And I should add, and I guess in here I won't bother rewriting this for you, but this would be meters per second. Put the unit in after the magnitude, and then the direction gamma, 71 degrees. And again, the gamma is my invention. It is meant as a compass angle instead of a theta. So sometimes you'll see these things written as, say, 5.2 and then angle 18 degrees. But this angle here is a theta, okay? It's not a navigational angle. So we want to differentiate between implying a theta angle or an XY angle and a navigational compass bearing angle. Alright, so there you have it. That's an average velocity question done with 2 straight line vectors. So now we'll move to 2 other questions that have curved paths. We'll do at least one of those anyway. Probably that's enough, I guess, for this type of course. Show you how that's done. So this is a typical question that you might get related to average velocity or average acceleration in this case. That is a curved path. It is a circular curve, so we don't have to try too hard. Often the speed is taken as constant. You find the speed going into the curve. They might give you the radius of the curve, and then they would ask you what the average velocity is. So you might say to myself, my gosh, okay, where do I start? Well, we know the definition of average velocity, or in this case average acceleration. So let's put that down just for, this is just the thinking page here, just to give us a sense of what we're trying to find out here in the sense of constraints. So this is by definition, the average velocity is delta v over delta t. So what we need to do is to find delta v and delta t. There's no time given in this question, but we can infer it. We know how fast we're traveling, and given that we know the radius and it's a circle, we can find the length of this arc. So if we find the length of this arc and we know how fast we're traveling, we can compute the time. So that is known to us. The delta v, once again, must be computed separately. One, a delta v for the x and a delta v for the y. And this is a bit different because we're going to look at the delta v. We're going to have the speed or velocity here and the velocity here, and we're going to have to subtract the two because it's a difference between these two. So it's a little bit different situation. The fundamental constraint of a question like this is simply the definition. What you have here is the definition that forces the answer, because it isn't simply a definition question. It is what is the average acceleration, and that is defined by the equation here. The technical definition now is what is delta V in this question? What is delta T in this question? And that's where you have to do a bit more thinking from your standpoint of your physics. Okay, so we'll do a little more here. Okay, so I've done a little more with this question now. So first, we have the 50 kilometer an hour initial speed. For that to meters per second, we get 13.9. We find the circumference of the turn is 2 times the value of pi, rounded to 3, times 20, the radius of the circle, 125.7 meters. And we only have a quarter of the circle, so we take a quarter of it and get 31.4 meters. So that's our distance. We have a constant speed of 13.9, make the division, and we're in the corner for 2.26 seconds. So we'll remember that number. And then we look at our initial velocity. In this case, is we know we're going straight up. So our x motion is 0. Our y motion is 13.9. We'll make it positive because it's going this direction, the customary up direction. We then, the final velocity over here, which is VF on this side, heading this way, is going to be positive in the x direction, as we typically do, and it is not moving anymore at all in the y. So those are our two velocities. The definition of delta V is VF minus VI, always final minus initial. Okay? So just subtract the ordered pairs and you get 13.9 minus negative 13.9 meters per second. And that's our delta V. So we're almost done here, but I've ran out of space, so we'll rub some stuff out and do a bit more. We have our delta V here is this ordered pair, and this will be divided by this. So once again, we have our average acceleration is delta V over delta T. And of course, dividing by delta T is the same as multiplying by 1 over delta T, which makes it a scalar multiple equation, which is perfectly okay. We can do it this way just because it's easier for us to read. So we're going to divide each of the coefficients, each of the vector components, by the 2.26. And we get plus 6.15 in the x and negative 6.15 in the y. Now given this is that a g, one gravity, is 9.8, just for sport, this is a pretty abrupt corner, so this would be kind of more of a racing type situation than what would be normal for the family car. If we now convert this to navigational methods, a lot of this is just intuitive. We're going to convert this this squared plus this squared square root and get us this. If you've played with this bit, you know the magnitude's the same, so you just multiply them by 1.414 and you get the answer. And then the direction, well, we have a direction in the x and going south that makes it southeast, since these are equal. So our direction is southeast. So what you can see, if you remember the original description, is that the acceleration is acting towards the center of the radius. Okay? And it makes some sense if we think about it for a moment. We originally had a velocity in this direction, and now we're going this way. So this velocity here had to be completely nulled out in the y, hence the negative. And it had to be completely transformed from no x motion at all to the substantive x motion. And so we need a fairly positive value here for the x. If we, and I'll let you consider, if we only went a quarter of the way around, let's say we went only to here, okay? How would this affect the results we get? I'm going to let you consider that and see if it's the same. And one mistake that many young people get in these cases, and you have to be very careful, is when we tell you the speed is the same throughout the corner, they're going to say the thing is not accelerated. And unfortunately, even though it's in the notes and it's in presentations like the one I'm making now, students don't spend enough time staring at this to learn the definitions. And you have to appreciate that if your velocity vectors, your components change, The only way these can change is through an acceleration in the x or in the y. The only way that stays the same, and if there is any acceleration at all, then of course the motion is accelerated. To convert these by going from this direction to this direction, you have to have values here. And when that happens, you're accelerated. So you have to, if you just remember the simple way that if the direction changes or the magnitude or both, you're getting acceleration. Okay? So again, the new idea is you have to read and read and read some more until these new ideas become better understood. And that is, of course, your technical knowledge. As I said earlier in this question, the average acceleration is a simple technical definition. And where we fall down is when we forget to follow those and go back to the language we're used to in the cafeteria, which will lead us astray. So hopefully the foregoing video was helpful to you in clarifying some of the issues with respect to 2D motion, especially average velocity and average acceleration. When we move on now, the next video will deal with navigation questions, both straightforward ones and more difficult ones, and then would then end this unit on 2D motion. So again, thank you so much for watching, and in the following slide you'll see my email and my webpage. If there's any comments or questions, please don't hesitate. Thanks again for watching.